periodic table. Okay, we are looking at how a bond is like a spring. And a stiff bond, or a stiff spring, which means a strong bond, vibrates at higher energy, has higher energy vibrations. As we go from a carbon-carbon single to double to triple bond, it vibrates at higher energies, higher frequencies, which is higher wave numbers. Frequency is proportional to K, which is the spring constant or the strength of that bond. Second factor here was the hybridization of the atom. So for example, carbon going from sp, half s character, tighter, closer, stronger bond, to sp3, 1/4 s character, slightly less of a strong bond. They vibrate at different frequencies, different wave numbers, and it can help us figure out what types of bonds we have in our molecules. So looking at this spring constant equation, looking at the vibrational frequency of that spring, which it matches the type of IR light frequency that it absorbs, we have K, the spring constant, and we also have mu, the reduced mass. So it's a way of taking the mass on one end of the spring, the mass on the other end of the spring, and doing a very simple mathematical combination to have one mass number to put, not a mass number, one mass value to put in your equation. So for example, here we have carbon bonded to different atoms. So hydrogen has a molar mass of about 1 gram per mole, carbon around 12, oxygen around 16, bromine around 80 grams per mole. As the mass of the atoms increases, or as the reduced mass increases, we can see that mu, that reduced mass, is in the denominator. As that value gets bigger, then the frequency of that vibration, which is directly proportional to the energy, gets smaller. So heavier atoms vibrate at lower energy, lighter atoms vibrate at higher energy. So using this equation can help you explain some of the trends that we looked at when we were looking at table 5.2.1 in our workbook. We're going to be referring to that table throughout our class today. So now we get to put on our detective hats. We're going to be using that table, and we're going to be analyzing different IR spectra. We want to see what peaks are there and what peaks are not there, which peaks are absent, and that gives us clues about what sample produced that IR spectra. Okay, so you can see in your workbook, we have a whole bunch of spectra that we're going to go through. This is the second time we've seen this IR spectra. We already chatted about it, but for thoroughness, we're going to very quickly remind ourselves. On the x-axis, we have wave number. It's in per centimeters. It's that it's not frequency, but it's that symbol with the little hat on top, which tells us it's 1/lambda, and it's proportional to energy. So we have the higher energy region over here and the lower energy region over here. We're shining IR light of all of these different wave numbers by our sample, and we're measuring the transmittance. If we have a 100% transmittance, all that IR light at that wave number goes right through the sample. It doesn't interact with it. But if that transmittance goes down, maybe to like 10% or 20% or 50%, whatever number, we can see the transmittance is lower, which means the absorption has increased. That means we have a bond that has a normal vibrational frequency at that wave number that can get excited and absorb that energy and lead to a peak. So here is our first peak. This big peak right here tells us that we have an sp3 carbon-hydrogen stretch. I'm going to send table 5.2.1 in my workbook over here. It's really helpful to go flipping back and forth, so keep this one available. You don't need to memorize this table. It's provided to you on your final exam. Refer to it when you're doing your practice problems. So don't memorize it, but know how to use it and know how to explain the patterns that we see as well. So here we see an absorption peak just less than about 3,000 wave numbers. And it's a very bold peak. It's intense, it's strong. Here we have our alkyl or sp3 carbon hydrogen stretches, and they absorb in the 2800 to 2950 region. So you can see it's just less than 3000 wave numbers. The alkenyl is just over 3000. Alkynyl carbon hydrogen is much over 3000. And these ones are broad. So here, this is telling us that we have sp3 hybridized carbon. The bond vibration that we're seeing here is the carbon-hydrogen bond vibration, the sp3 carbon hydrogen, and it's medium to strong. This one's really obvious in its intensity. If we draw out this molecule here, you can see it has 14 plus 2 carbons, so 16. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. It's really big. I'm not going to draw in all the hydrogens, but I'll draw in a couple so you can see how these sp3 hybridized carbon-hydrogen bonds are producing this sp3 carbon-hydrogen stretch. This peak tells us that we have that carbon-hydrogen stretch. We talked about how this region is the diagnostic region or the functional group region. It's usually fairly obvious to identify peaks in this region. Once we get below about 1500, we're in the fingerprint region. And as we go along, you're going to see it kind of turns into a mess sometimes. This one is really clear, so we can actually see some bends. Remember how we talked about bond stretches, but we also have some bond bends? This is a bend that's happening with the CH2 group. These ones are in the fingerprint region, so moving forward, it's going to be difficult to identify those bends. But because we have this peak, just less than 3000 wave numbers, we know we have an alkane. Okay, now let's compare that to an alkene. If we go, actually, I'm going to go forward here. So here's our alkene and our alkane. Ene, ane. Double bond, single bond. This is the one we just did. The most unique peak that's different between the alkane that we just identified and the alkene is that sp2 carbon hydrogen stretch. How do we know it's an sp2 carbon hydrogen stretch? We can see it's just over the 3000 wave number line. So if we drew a line up here at 3000 wave numbers, we can see the sp2 carbon hydrogen stretch is just bigger than 3000. We're talking about, here is our sp2 hybridized carbon. So we're looking at these carbon hydrogen stretches and this carbon hydrogen stretch. But then we can see we have a bunch of other, 1, 2, 3, 4, let's count it. 1, 2, 3, 4, 5. I went too far. 1, 2, 3, 4, 5. Then we have our sp3 carbon hydrogens over here. Let's use a different marker. So we still have sp3 carbon hydrogen stretches. That's all of these ones over here. But in red, we've highlighted the sp2 carbon hydrogen stretch. Here, if we have an alkenyl group, which we do, the carbon hydrogen for the sp2 absorbs just over 3000 wave numbers, and we see that peak. It's a medium intensity. You can see it doesn't go all the way down, but it's not a tiny little blip. It's medium there. For an alkenyl functional group, we would also expect a carbon-carbon double bond stretch to happen around 1650 wave numbers. It might be strong, it might be weak. So this one isn't super obvious all the time, but this is a fairly simple molecule. The only interesting thing about it, besides the alkyl groups, is the alkenyl. So this carbon-carbon double bond around 1650 wave numbers, we can certainly identify. So here we have our carbon-carbon double bond stretch, and that's the vibration between the two sp2 hybridized carbons, this double bond. We have some bends in the fingerprint region as well, but those ones are harder to identify. So we're going to focus on the stretches happening in the main diagnostic region. Okay, so alkene had that extra sp2 carbon hydrogen. Alkane didn't have that. Now we're going to go to alkyne, and I'm going to flick back and forth. Alkane, whoop, alkane, alkyne, alkane, alkyne. Here we can definitely see a unique peak happening that is not in the alkane region, and we can see it's around 3,300 wave numbers or so, and that falls under our sp carbon hydrogen stretching, around 3,300 wave numbers, and we can see its relative intensity is strong. You can see that this peak stands out. It's bold, it's intense, it dips quite a ways down, so it's easy to identify. It's very diagnostic. So this is our sp carbon hydrogen stretch. Now notice only one of these two carbons has a bond to hydrogen. The carbon on the right just continues on with the carbon chain. So it's only this one sp carbon to hydrogen bond that produces that really intense peak. Well, in addition to that, we can still see just less than 3,000 wave numbers are carbon hydrogen stretches that are in the sp3 category. If we have an alkynyl group with that triple bond, we've already identified the most diagnostic peak, the sp carbon hydrogen. We can also identify the carbon-carbon stretching that has that triple bond, and we're expecting it to absorb in the around 2,200 wave number. And sometimes it's intense, sometimes it's not very much, it's variable. And here we can see it's not too intense, but it's still identifiable here. So we have our carbon-carbon triple bond stretch. Okay, so we've identified alkanes, alkenes, and alkynes. And then we also have our aromatics. Now, for this molecule here, we have our sp3 carbon hydrogen stretches. And this is one that you're getting very used to, hopefully. Just less than 3,000 wave numbers. We have our sp3 carbon hydrogen stretches. But more unique, that makes this one stand out, is we also have sp2 hybridized carbon hydrogen stretches. The carbon-carbon bonds here have a bond order of about 1.5 because it's a double, single, double, single. It absorbs in around 1,500 wave numbers, which is what we see here. Okay, so we're now able to distinguish between alkanes, alkenes, alkynes, and we can find similarities with those aromatics as well. Okay, so now let's move to our alcohols. And in our table, you can see that OH stretch for alcohols is identified as broad and strong. And so I would say that this is the most obvious peak that we have. You can see it is indeed very broad, very strong. It falls in the expected wave number region, around 3,200 to 3,500 wave numbers. And this is this oxygen-hydrogen stretch in this part of the molecule. It's very bold, very obvious, and it tells us that we have an alcohol functional group. Here, again, just less than 3,000 wave numbers, we still have our sp3 carbon-hydrogen stretches. And then we have some bends happening in the fingerprint region as well. But obviously the most diagnostic is that OH bond vibration, absorbing in that region. Okay, now let's move on to our amines. Here, the unique peak that we're adding to our repertoire here is our nitrogen-hydrogen bond stretching. This happens, as we can see in our table, in the 3,300 to 3,500 wave number region. So it matches what we would expect. This nitrogen here is a primary amine. It has 2 nitrogen-hydrogen bonds, and it just so happens that it produces a double peak here when it's a primary amine. You can remember this because it has 2 nitrogen-hydrogen bonds. The reasoning for this is a little bit more complicated, but remember, 2 nitrogen-hydrogen bonds for those primary amines gives us this double peak. You can look for that characteristic double dip happening there. We can still identify other important components of this molecule. Just below that 3,000 wave number region, we have our sp3 carbon-hydrogen stretches, such as here and here, and there's more of them. You can draw them all in if you like. And we have some extra peaks happening in this region just above 3,000 wave numbers, which tells us we have sp2 carbon-hydrogen stretches as well, and we can draw those in. So it's really helpful if you have multicolored pens today. We also have a carbon-nitrogen stretch happening over in the fingerprint region. But this doesn't show up in our table of values over here because it's not diagnostic. As soon as you have other functional groups happening, it can kind of get buried. So it didn't show up in your table of values. Okay, so these are our primary amines. We're looking for that double peak. Look how this primary amine peak, even though it falls in the 3,300 to 3,500 wave number region, see how the alcohol also follows in an overlapping region, 3,300-ish, 3,300-ish, but the amine peak is medium intensity and it's double or single depending on primary or secondary. Look at that hydroxyl. See how big and bold it is? So even though they fall in the same region, we can distinguish between alcohol groups and amines because they have different shapes. Okay, now let's move to secondary amines. Here we have a nitrogen-hydrogen stretch. It's in the same region, around 3,300 wave numbers or so, but this only has 1 nitrogen-hydrogen bond vibration, and we only see 1 peak, not that doublet peak that we saw with primary amines. And of course, we can still see our sp3 carbon-hydrogen stretches. And you're going to find these are present in most of our organic molecules. Many of them for sure. Ready to keep going? Making sense so far? Just kind of matching the table and seeing how it applies in these real spectra. Okay, what about tertiary amines? How many nitrogen-hydrogen stretches or nitrogen-hydrogen bonds are in tertiary amines? Show me with your fingers. 0, that is correct. It says 3, so you might think 3, but it's 0. A tertiary amine is when we have a nitrogen to a carbon, to a carbon, to a carbon, and then it can go on and do whatever. But there is no nitrogen-hydrogen bond in a tertiary amine. Therefore, we're not going to be looking for an amine peak in that region. So this region is only going to tell us about primary and secondary amines. It is handy to have that carbon-nitrogen stretch that we can see as well. But again, it's in the fingerprint region. Okay, now let's move on to our carbonyls. I want to draw your attention to this table. The aldehydes, ketones, esters, carboxylic acids, they're all in this portion of the table because they contain that carbon-oxygen double bond. And see how they're labeled with relative intensity as strong. These ones are very diagnostic. So this carbon-oxygen stretch happening around 1700 wave numbers, it can shift slightly depending on which group it is, but it is very bold. See how it's narrow and it's very intense. That's what you're going to be looking for with the carbonyls. It even has an overtone happening where it jumped like 2 energy levels. It's like double the wave number increase there. So here with the ketone, we're looking for that very bold C double bond O intense peak. And again, just less than 3,000 wave numbers, we still have our carbon-hydrogen stretches happening. Okay, so this one is a ketone with that bold carbonyl peak. Now we can also find this in an aldehyde. I'm going to go back to a bold color. Again, around 1700 wave numbers, we can see that characteristic carbon-oxygen double bond happening. You can see that it's also getting in the way of some of our carbon-carbon double bonds, which is actually like 1.5 bond order. Both are present for this molecule here. We have a little bit, just less than 3,000 wave numbers. We have our sp3 carbon-hydrogen stretches. We have some sp2 carbon-hydrogen stretches from this aromatic group happening here. And we even have some rather unique carbon-hydrogen stretches happening from this aldehyde over here. So ketones, that carbon double bond O, the carbon has a single bond to carbon and a single bond to carbon. Aldehyde, one of those bonds is to a hydrogen. And that carbon-hydrogen stretch for the aldehyde falls around that 2800 wave number region. So just below the sp3 carbon hydrogens. But again, primarily we're looking here for that carbonyl stretch happening in the 1700 wave number region. Okay, let's keep going. Now let's look at carboxylic acids. Carboxylic acids contain that C double bond O. They have that characteristic carbonyl stretch. This is why carboxylic acids is listed towards the bottom of your table here, around 1750 wave numbers, and it's very strong. And we can see it does contain that carbonyl group. Importantly, carboxylic acids also contain the OH group, this characteristic stretch. OH groups, when it's an alcohol, it's just kind of shifted up to like the 3300 to 3500 wave number region. When it's in a carboxylic acid, it's shifted down a little bit, but it's still very broad and very obvious. So when we look at our table to recognize that OH group could be in an alcohol we saw it's broad and strong around 3,300. Or if it's in a carboxylic acid, that same OH group, because it's also close to that carbonyl group, absorbs less than 3,000 wave numbers. Okay, so it's still really broad, but alcohol, it's here. Carboxylic acid, it's over here. Now I've drawn in the OH stretch as a red line here, but you can see it's also overlaid with this sp3 carbon-hydrogen stretch, because this contains lots of sp3 carbon-hydrogen bonds. That's why we get the funky kind of like, it looked like it was big and bold, then it has like little dips and zigzags at the bottom. It's because it's overlaid together. We have sp3 carbon-hydrogen and we have hydroxyl stretching happening around the same region. But we can identify it because normal sp3 carbon-hydrogen stretches are like this, and now it's much broader, and it has that carbonyl stretch. So we want to look for all of these clues, and based on that combination, we can identify this as a carboxylic acid. We're almost done. Okay, let's get to esters. Esters also have that very bold carbonyl stretch that we want to look for. This particular one, that carbonyl stretch is kind of close to some carbon-carbon double bond action happening. We still see our sp3 carbon-hydrogen stretches, and just over that 3,000, oh, let's choose a different color, just over that region, we also have some aromatic carbon-hydrogen stretches. The carbon-oxygen stretches that we have here are in the fingerprint region. So we can identify them here, but again, it would be the best diagnostic tool. Okay, discussion activity. I'll give you like 45 seconds. Chat with the person beside you. What features would you look for in an IR spectra of aspirin? Here's the structure. What kind of peaks would you expect to be present? Chat with the person beside you. And 3, 2, and 1. Okay, this is a good exercise when you're critically problem solving some spectra. Sometimes it can be overwhelming to just look at the spectra and try to figure out what's there, what's not. Sometimes it's helpful to think, what am I expecting to see? What type of functional groups do I have? What am I anticipating? And it can help you to identify those features in the spectra. So you probably observed that it contains an OH group. And again, we have that broad OH group happening here. You probably anticipated that it had sp3 hybridized carbon-hydrogen stretches happening. And indeed, we see that there. More importantly, you identified probably that it has a carbonyl group, one from the ester, and it has another carbonyl group from the carboxylic acid. I admit it's getting a little messy at this point, right? Oh, it has lots of features. It has an ester, it has a carboxylic acid, it has a carbonyl, but we can identify many of these components. And if you were working in a forensics lab and you had a powder and you didn't know what it was and you ran its IR spectra, you're going to be able to find this exact spectra with that exact fingerprint region in a database. And that will also help you to identify what that molecule is. Okay, I want to get through this problem, so let's do it. We want to do the final example here. Match these 3 molecules to the IR spectra that you have. To begin, which features would you expect across all of these IR spectra? Who can just shout out a feature that all of them should contain? Aromatic, that's right. We're expecting an sp2 carbon-hydrogen stretch for all of them. So that isn't going to help us differentiate these. What else would we expect in all of these? Yes. An sp3 carbon-hydrogen stretch. Indeed, they all have that. What else? Yes. An aromatic carbon-carbon. That's right. We're going to expect that. So chat with the person beside you. This is spectrum B that I have on the screen. So make sure you're looking at the right one. You have A, B, and C in your workbook. I'm pulling up spectrum B. Which molecule produced spectrum B? Chat with the person beside you. Look at peaks that are present, peaks that are absent. And I'll give you 10 more seconds. And 3, 2, and 1. Okay, 3/4 went for B, and I agree. The unique feature here is that amine, that primary amine peak, it's nice and diagnostic because it's that double peak that we have happening there. It could have been confused a little bit with this peak over here, but this one is just our carbon-carbon 1.5 bond. One more iClicker question. Let's do this one. Work with the person beside you. This is now spectrum A. Which molecule produced spectrum A? And 10 more seconds. And 3, 2, and 1. Okay, moving towards 90%, went for C. C is correct. We have that bold carbonyl peak, which means the last one, spectrum C, is our alcohol group. Have a great day. Bring your model kit next class. We're going to be using it, and I will see you then. Take care.